And in this way, so if you look at the diagram there, we have 3 keys. So we have key 1, key 2, key 3. And in key 1, we have a memory allocation. So what we are saying is that each data type, each linked list or element in the linked list has 4 critical characteristics, 3 critical characteristics. It has a key. So in the box in front, we see the key. So we have key 1. The data in the key is 1, 2, 3, and the next pointer is pointer with a number in parentheses 1, 0, 0, 0, 1. Where we have a null pointer in the next pointer, that is where the program terminates. So as this way, the linked nodes allow the linked list to grow as needed and use non-contiguous memory spaces. In some programs, when you write, you require that the processing use a contiguous memory space. What it means that all the processes are stored in a single space in the memory. Where it is non-contiguous, it means that the storage of the processes are done in different parts of the memory, and that is where linked list becomes critical in programming. And if you later on, we'll see how they are implemented. And linked list has very important terminologies that we have to understand. First, equal time random access. When we talk about linked lists, we say that all the lists have equal time random access. What it means is that the element or in the array takes the same time to be accessed, irrespective of where they stored in the memory. So equal time random access means that any array element takes the same time to be accessed. Then when we say now in linked lists, it's a term that is used to denote a reference to an invalid or a non-existent object. So if you declare a non-existent object or an invalid object in your linked list, it's referred to as a null. Then the head pointer is a pointer or a reference to the first element in your linked list. And the tailor pointer reference is the last element of your linked list. These are very important things because in the way they are implemented, we see that these have specific implementation in C++, in other programming languages. So it is essential that you understand what they are. These also inform the reason why you use a linked list, a stack, or queue. So we see another example that has been provided here. In figure 3, we see that we insert a new node on the linked list first, right? And then the new node is created to hold the data. And once the data is accessed, the node requires a space in the memory. And the next link of the tail is updated. That is why we say it's dynamic. When you point to an item on the linked list or a node in the linked list, the first node is created to hold the data. Now, the node requires a memory space, and the memory space have an address that is pointed to. And then the next link of the tail is updated to indicate the links, the elements that have been used. There are 2 forms of linked list. We have a doubly linked list, and then we have a singly linked list.
Please, sir, can you go over again?
So you see, when what I'm saying is that linked list is a dynamic abstract data type. when we say dynamic, it means that it is not a static element in the array. It's not a static element that you that are provided in the list. It can insert, it can delete, it can delete. So what it does is that when you make a system the call, when you make a system call, you start with the insertion of a new node, right? That will be linked first. Then when you point to the new node is created in the linked list. And this linked list is stored contiguously in the memory, right? And it holds data. And as I said, it has each node has 3 components. It identifies the key, whether it's in key 1, key 2, key 3. It also has the data that it holds, and then it has the pointer. The pointer points to the next node that will be required. So the node requires a space in the memory. But once you point to the first list and a first element in the linked list, and the node is created, then once you create the pointer, then the next node is pointed, and then the last one is updated to indicate whatever processes that have taken place in that node. So as I mentioned, there are 2 types of linked lists. We have doubly linked lists. In doubly linked lists, each node has an additional pointer called the previous pointer that holds the address of the node that preceded the current node that you are pointing to. Then, but with a singly linked list, it doesn't have the previous pointer. It has the key and the next pointer only, but it doesn't contain the previous pointer. The previous pointer comprises the doubly linked list comprises nodes with the next and previous pointer. The previous and the next pointer allow moving from head to tail or tail to head. Along when we move on, you see you see when you go through the nodes, you see there's some examples of a circular link. Then we also have stack. When you think of a stack as a linked list, where you see you can queue. A queue is linear from one front to the back. By a stack is also linear, but stack start from top to the bottom or bottom up. When you're making you're accessing a queue or a stack, you use different modes to do it. So whereas in the normal linked list and a queue, we can insert, we can delete. In stack, we cannot do that. In stack, it's characterized by 2 operations. That is the push and the pop operations. So you can think of stack as a linked list where the elements are added and removed only at one end, much like adding or removing books from the tops of a stack of books. Whereas in linked list, you can insert from front or the back. With stack, you can only insert from the top only. So there are only 2 operations when it comes to stacks. You can have push, a stack, and then these are reserved words in C++, and you have a push and a pop with parentheses. So the diagram here is showing a stack of books and how you can push a book or you can pop a method that you can use to pop a book. An algorithmic example has also been provided in the stack selector that I have sent you. When you're dealing with stacks, we also have specific, very important terminologies that I want you to bear in mind. That separates stacks from linked list and from queues. In stack, we have a schedule policy. The schedule policy is the rule that dictates in which order the elements in the data structures can be retrieved. So the array and the list have a random access policy. There is no specific order to insert or retrieve an element. So a schedule policy indicates the order in which elements in the data structure can be retrieved. So when you have an array or linked list, in stack you use random access policy. And there is no specific, which means that there's no specific order to insert or retrieve the element. Then we also have overflow, stack overflow. Those of you who are good at programming, you might have experienced those problems where you have a loop that doesn't end. You're likely to experience stack overflow. And stack overflow, overflow is when you try to delete or retrieve an element from an empty data structure. So an underflow is where you try to delete or remove or retrieve an element from an empty data structure. Whereas overflow is when you try to insert a new element into a data structure with a size limit after it has reached its maximum capacity. So where you have an unterminatable loop, for instance, you have we mentioned that any process that is deallocated from the processes is stored in the memory, and therefore, if you have a loop that does not end, that is not properly constructed, or if you have a recursion that is not properly terminated, there will be consumption of the entire memory. And when the memory reaches its storage limit, then you are likely to have a stack overflow. So that is one of the commonest problems that we see in programming, errors we see in programming. Then we have queue. A queue is a linear data structure that behaves like a queue of people. The main characteristics of a queue is that it implements the first in, first out policy. What it means is that the first element inserted must be the first element that is retrieved. So queue has two main operations, and it is on queue.
It's not going on. It's still
The
at,
slide is not.
it's still at stacks.
Are you sure? You haven't seen queue?
No, sir.
Yeah, he should check his connection. You are still on the queue.
Yeah, you check your connection. Maybe. So a queue implements the first in, first out policy. So in the memory, whatever element that is inserted first must be the one that is retrieved. And like stack, Q2 has two main operations. It has the on queue and then queue and then the dequeue operations. So what are some of the common linked list operations? These are some of the things, the very important things. We are going to look at the various operations of these three summaries that are done. When it comes to linked list operations, the common ones are that a linked list are a great model of a dynamic structure. Many of the principles used to operate them are critical to operating on more complicated data structures. And one aspect that makes linked lists so valuable is the flexibility. So if you use the appropriate procedure, you can merge, you can join, you can have an intersection of two linked lists efficiently as possible. Because in the programming, sometimes in solving a problem using programming, you might have two separate lists, linked lists. If you follow the correct procedure, linked list operations enable you to merge, you can join, you can find an intersection, you can delete, you can insert linked list, so that you don't have to be creating separate static linked lists all the time when you're solving programming problems. So why do we use linked lists? We use linked lists because using arrays provide constant random access time, but inserting a new element in a specific position is difficult. So when you are in the beginning of your programming journey, we were taught how to declare arrays in the programming. That these arrays are stored in a specific location of a computer memory, and then we direct the program to access this array. And we've mentioned, as we saw earlier on, when you have an array, you can only access them randomly. And so you use random access at a time. But when you are trying to insert an element into an array, it is very, very difficult. So linked lists provide a more flexible tool by which we can insert additional or delete or manipulate arrays that we have in elements that we have in the linked list. But the elements that we have in an arrays are always accessed randomly, but it is difficult to insert a new element in them. And that is why we say that linked list is a dynamic abstract data type. Then linked lists also provide constant time unsorted insertion, knowing beforehand how large the linked list will be. Sometimes when you create a program, when you're creating a program, you may not know how large your linked list should be. Sometimes too you know, but then the problem that at hand, the problem that you're solving will require additional insertion of of elements in the linked list. If you declare array, you will not be able to easily insert these elements. But if you're using linked list, it enables you to easily insert these elements in them. So we saw doubly linked lists earlier on when we said that a doubly linked list have nodes that contain the next pointer and the previous pointer. But singly linked list, the insertion of a new linked element could be unsorted, sorted, random, or at an index. So when you are inserting a new element in a linked list in an unsorted manner, there are three options. You can insert at the tail, you can insert at the head or a front, or you can insert at a given index. So the examples of how we traverse a linked list by inserting in a sorted manner and then unsorted manner has been provided in the diagrams that you can see. And detail of algorithmic implementation have also been provided in the lectures that I've sent you. Now, when it comes to doubly linked list, when working with doubly linked lists, some singly linked list procedures are simplified since you have accessed previous elements in the list. So you can split a linked list. It is only necessary to change the pointer of the nodes where the split is done. So in a situation where you want to split it, you can only split from the previous nodes where the pointers have indicated. So it is easier to work with linked list than you cannot split an array in your program once they are declared. But once you have doubly linked list, you can easily split it and change the pointers from where you splitted them. So when you look at the diagram, you realize that we have some nodes that were keyed in key 1, and then after key 2, the linked list is split here, and then you have the pointer linked to the first node where the the linked list was splitted. Then we have circular linked list. Circular linked list is a doubly or singly linked list where the tail next pointer points to the head, and the previous pointer of the head points to the tail if it applies. So we have seen three types of linked list. We have seen a singly, doubly, and then a circular linked list. So in a circular linked list, you see that the next pointer points to the head of the list, and the previous pointer points to the tail of the list. So it's in a circular form. The illustration here, each node has a next and the previous pointer. The head has the previous pointer to the tail, and the tail has the next pointer to the head. Then we have common stack ADT type methods. Some of the common stack methods that are used in stacks. So any stack data structure must have two primary operations. We saw it earlier. We have the push and the pop operations. And the way these operations are implemented is of no importance as long as the implementation enforces the last in, first out policy. So in the stack, because we have only one point of making changes, insertion is that. So let me give an example of the method that stack uses. Is the last in, first out. If you're piling up books on the table, the first book to be put on the table will be at the bottom. So if you want to take these books out of, the last one that you put will be on the top. If you try to pull the first book that you put at the bottom, you are likely to drop all the books, or the stack will fall down. So stack implementation use LIFO. So the last in, first out, because the last element that is put in will be one that will be on top. So irrespective of the operations implementation that you use, so long as you use the last in, first out, you can implement stack methods. And stack can have a maximum size or grow as large as necessary, but these must be declared in the program. So where you have a limitation, you should indicate the limit of the stack. If you don't, then you are created a situation where you can have as large stack as necessary for your program. So theoretically, there is no limit for stack abstract data type, but it must be possible to add and remove elements in stack. So why do you use stack? So because stack is characterized by the last in, first out policy, the objects are returned in the reverse order in which you insert them. So I've given a physical example of the physical way of solving a problem. If you pack books on the table, the first book you put will be the bottom. The second one will be the next, the second one. So the last book will be at the top. So if you want to use the books for any purpose, it is difficult, impossible to remove the book from the middle. So you take the last book. So where you are implementing an algorithm where you need to use the last elements first, then you implement a stack as a way of solving the problem. So one way to implement a stack is by using the linked list. You can get a desired behavior by removing and inserting at only one end of a linked list. And it is possible to implement the pop and push operations using either end too. So the two main stack operations, we've mentioned them, are the pop, which removes an element from the stack, and push, which inserts an element into the stack. So the LIFO policy requires that the last element pushed into the stack must be the one to be deleted when the pop operation is used. So this is the diagrammatic representation of the stack operations. And when we use C++ algorithm, I've provided them in the lecture slides that I've already sent to you. So how do we said that theoretically the stack can be as big as necessary. But if you're doing that, what it means is that you are likely to create a stack overflow if you exhaust or if you exceed the maximum of the memory that is allocated for the program. And therefore, we can use a parenthesis to balance stack. So normally when we declare a string has parenthesis balance when every open parenthesis has a closing corresponding parenthesis. So you see we have the two brackets when we declare string. And to determine if an expression has balanced parentheses, the order is essential. So a stack can be helpful to keep track of how many parentheses are still open and in which order they should be closed. So when you open a parenthesis, it needs a corresponding close parenthesis. And if you're using stack, it makes it easier for you to identify the number of open parentheses that are not closed. And if you have open parentheses that are not closed, you're likely to experience a stack overflow as well. So we've seen queue, and we said that there are two general operations that is applied to the queues, and we have the onqueue or enqueue, and then we have the dequeue. Any queue data structure must have two basic operations. As with staff, the most critical aspect of writing and implementation that enforces the first in, first out policy. So whereas the stack implements the last in, first out policy, we know that queue implements the first in, first out policy. In some applications, you might want to restrict the queue size or even have a limit given by the implementation. So the important part is that the implementation provides an interface to the user through the onqueue and the dequeue operations. So why use queue? The first in, first out characteristic of queue makes it perfect for any shared resources where all requests have the same priority, or especially in memory management and where we are sharing processing and memory resources, and we have the same priorities for the program or for the processes. Then we need to implement queues, and the queue will distribute will perform the process based on the first in, first out principle. So the diagram here shows a series of schedule of processes in a computer. The computer process, in the computer processes. When you sit on a computer, you are a user. You send a program or a command that enters into a job queue, and from the job queue, the process enters the CPU, and from the CPU, the process may require input or network. In such case, it enters in a different queue. If it requires a network, if it requires an input, it enters a queue. Otherwise, the process implements a first in, first out. And so sometimes when you are working on your computer and it freezes, and it freezes, if you remember your operating system, you identify a problem called a deadlock. A deadlock can freeze your computer in the sense that most of the time processing utilizes the queue, and it uses the first in, first out. And if there is a resource that is required to process the current thing, and that process or that resource is locked up in another process, then the whole computer processor will stop and wait for the release of that resources that can be utilized to complete the processing of the current process, and therefore there can be deadlock. And that when your computer, that is when your computer freezes you can use the Control-Alt-Delete command and then identify all the processes that are going on. And if you see a particular process that is not responsive or that is consuming a lot of resources, you can end that process. You can click and end that process, and they will release the resources to the queue that will be used for the next processes for your computer to work. So queues are very, very important in processing, efficient processing management as part of the functions of your operating system. So we've said that there are two primary operations in Stack that are on enqueue and the dequeue. So the enqueue operation inserts a new element into a queue. So if you have enqueue q, x in parentheses, what it means is that the operation will insert a new element called x into a queue called q. And when you have dequeue q, the operation deletes the first element inserted or enqueued into queue. So when you want to print an element of a queue in a reverse order, queues are great for modeling anything that behaves following the first in, first out structure. So when you issue a print command, when your computer is processing, when your data file, you want to transfer data files to the different storage media, all these processes use the queue, and they use the FIFO, the first in, first out principle. One of the challenges of queues and Stack might be that they don't provide enough flexibility to change the orders in their elements. So one of the strategies that we can use to manipulate elements in queue and Stack is to use what we refer to as auxiliary data structure. An example of this have been provided in the diagram. When you look at it, you understand when we meet, you have challenges, we will also discuss them. So when we look at data types, we will realize that we can have arrays-based Stack and queues. And when a small number of elements of a single data type is stored in a stack or queue, it becomes unnecessary to use a complex dynamic data structures as a base, right? So then when it happens like that, then a static data structure might be good enough because the stack or queue doesn't need to grow beyond specific limits. Simply put, we know that array is made up of elements with the same data type that are fixed, that are stored in the computer memory that is required to complete a process. And so in situations where we don't need dynamic data structures, it is enough to implement array that give you the static data structure. But we can have a stack and queue implemented using an array as a data holder. That means that the data that will be stored in an array. But to be able to do that, those data that will be stored in an array implemented as queue or stack must be of the same data type. An implementation of stack with array has also been provided in the diagram below. So for stack implementation using array to have a stack properties, it is necessary to keep the index at the top or use a particular value. So two things are necessary to enforce the first in, first out policies and use all available spaces in an array. First, you need an index for the tail or head of the queue. And second, there must be a shift in the position of the element in the array. So you must shift an element in an array during the onqueue and then the dequeue operations when you declare them. So the diagram here also shows how you can implement queues with arrays. So these are a comprehensive summary of the three. It is important. These are the most important things I want you to know that are examinable, because in the morning when I was preparing for the lecture, your class rep told me what you're going through this semester. So I'm trying to make the lectures as simple as possible, but I also have to fulfill the requirements of the course. So I've sent you the three lectures that have been summarized into the lecture here. Those of you who are interested, who want to be able to implement them using algorithms, I've provided them in the other lecture, and then I've provided the diagrammatic representations also in this lecture. And these lectures will be made available to you during revision week. But I want you to look at the detailed one there might be, so that you get good understanding of what we are doing and how they are implemented using C++. Okay. Any questions? Or we reserve the questions for next week, right? All right, so if there are no questions, then we will end the lecture, and then we'll have to have at least 3 more meetings to finish, and then I'll send you sample trial questions that you can look at the end of each of the summaries that I will do for you. Please. It is important that you read details. One, do it. I know you're stressed and we didn't start early, but I want you to benefit from the course, not just pass through. So enjoy your holidays, and then I'll coordinate with your class rep when we can have another lecture in the course of the week, before week on Thursday.
Thank you very much. Thank you very much.